It's moving toward Anna and away from Bill. So now when the horn is blown, well, what starts out as a spherical shell immediately gets distorted because the train's moving along, so it's compressing the shell on this side and stretching it out on this side. So if you think about it, here it's becoming a shorter wavelength toward Anna, here toward Bill it's becoming a longer wavelength. Well, that's what we see with the Doppler effect, shifting to a longer wavelength here, moving away from Bill, and shifting to a shorter wavelength here as it's moving toward Anna. You ever heard the same thing when, say, a fire truck goes past you? You hear the truck, and just all of a sudden there's the siren, and it starts getting louder and louder, and the pitch goes up. And then the minute it goes past you, the pitch drops and it starts getting quieter. Right? You know, there wasn't somebody in the cab with a switch that did that. That was the Doppler effect. It was shifting from this compressive, shorter wavelength to all of a sudden, boom, longer wavelength, and the sound level and the pitch dropped accordingly. Okay, so that's what Hunson and Hubble were seeing. And basically, when they look at a star that was positioned just so that the way Earth and the star were moving through the universe, it appeared that the star was stationary to Earth, relative thing. And they would get a spectrograph on that and use that as their baseline spectrograph as a star that wasn't moving. And then they'd start looking at the other stars that were moving. And every time they looked at a star that was moving, they got this red shift toward the red end, toward the low frequency end of the spectrum. So that meant, just like the train going away from Bill, things were moving away from Earth. So all of these stars were moving away from Earth. Kind of neat, huh? The red shift on the spectrum gave them that. And every star they looked at that was moving around was doing this. Now, does that mean that Earth is the center of the Big Bang and everything away from us like that? No. Because when you look at the stars in relationship to each other, they're all moving away from each other too. Everything's expanding. The distance between everything is getting bigger. It's like raisins in the dough for the raisin bread. It's just all sitting there, and you put the dough in the oven, and the yeast begins to work, the bread expands, and every raisin in the dough moves away from every other raisin. It's expanding. So the Earth isn't the center point. It's just one of the many things that's expanding along with everything else that's moving away from everything else. Pretty cool science. It's nothing spectacular. It's just some neat basic spectrometry collected over a long period of time looking at a lot of stars. And we're still doing it. So the Big Bang is expanding. The universe is still going on, still expanding. And we're still trying to map it out, figure out what's happening. And right now, it looks like the date we're kind of focusing in on is somewhere around 13.8 billion years for the beginnings of this rapid expansion. So we're kind of maybe figuring it out. Now, there are a lot of tweaks. This isn't a done deal yet. It looks like a pretty solid theory, but there are going to be some surprises and changes as we keep working on it. That's the way science works, right? That's the scientific method in action. It's going to be exciting. You guys are going to have a great life watching this stuff. It's cool. So what happened? We started with nothing but energy in the laws of physics. There was no matter. Nothing existed. It was just all energy. How did matter pop into the picture? Well, remember Einstein's famous equation? I bet you can all say it. E equals mc squared. Energy equals matter. And that matter is multiplied by a constant c, which just happens to be the speed of light, which is a big number to begin with, and then you square it. That's a really big number. So that means that it takes a whole lot of energy to make that mass. But in order to convert from that energy side of the equation to the mass side of the equation, I've got to somehow cool all this energy down, slow it up, so it has a chance for things to kind of come together and stick together. And that's what happens after the initial phases of the Big Bang. We start to see things cool down. And as things start to cool down, we start to be able to put minor little particles together, and eventually we build atoms, and atoms start to build bigger elements, more complex elements. Now, have we slowed everything down since the Big Bang? There's one of the big questions. The idea was that the Big Bang would start out and then it would kind of slow up as it ran out of steam. But what we see with the measurements we've taken since 1929, when Hubble and Humason started this, is that things aren't slowing up, they're actually speeding up. So that means we're still in somewhat the initial stages of this Big Bang, where it's still taking off. But it has cooled down enough, despite the speed, to make matter. So this really puts together two big questions now. And that question kind of revolves around, how's this Big Bang going to end? If we're speeding up, does that mean it's just going to keep speeding up and things are just going to keep flying apart forever and ever? The open-ended idea. Or is it like we really originally thought that, it's eventually going to slow up, run out of steam, and then finally the mass, the gravity is going to start pulling it all back together again. It's going to speed up as things get closer, more gravity, boom, and we all go back into just pure energy. And that gets to a point where it just keeps compressing and compressing, and all of a sudden, boom, out it goes again as it goes critical and re-explodes, quote unquote. So we have cycles of Big Bang, where it just goes out, comes back in, goes back out again, comes back in. That's the closed theory. And that's the big question planetary astronomers are trying to figure out right now. Which of those is the cycle? So if we're just in one cycle of one Big Bang, that kind of says our universe is just a little thing, just like our solar system is a little part of our universe. Our universe is even a smaller thing, part of just one cycle of a whole lot of Big Bangs. And we might understand that a lot of those happen, but there's no evidence left of any of them, is there? So it's kind of a neat philosophical question, but it's going to be pretty tough to answer. Okay, so here we are. We're in the cycle of Big Bang. It's starting to make matter. What kind of matter are we going to start to make? So let me give you 15 seconds to answer this question that I'm sure you've already had plenty of time to think about. Okay. Ready? Let's tell you. Yeah, simple. And somebody answered these. Indecision. Yeah, think of our life. We all started out as infants. We couldn't even see when we were first born. And we have simply grown and developed and become more and more and more complex. And we continue to do so. We are the most complex species on the planet. All the species before us have been less complex. So it makes sense. You start simple and you build on that. Oftentimes, just taking two simple building blocks, putting them together to make the next level of complexity. Take two of that level, make the next level of complexity, and the process continues. And that's the way it was with the beginnings of the universe. We started simple, and got more and more complex. So, here's the periodic table. I bet most of you remember this, or dreaded it in chemistry in high school. And here we are with hydrogen. Atomic number 1. That means there's one proton in the nucleus. The absolutely simplest element out there. So we probably had a lot of hydrogen to begin with. And then if I take two hydrogens and smash them together and they stick together, that means I'm going to have a proton from each of them now in the nucleus. So I'm going to have a nucleus with two protons, and what I've done is I've just made helium. And if I took a helium and another hydrogen, I could smash them together and get 3 protons and make lithium, or I could take 2 of helium and get 4, and the process continues as I continue to put together and build the periodic table. Mendeleev really was pretty smart in the way he laid this out. When he did this, he didn't know all of these different elements. He left gaps in the table for them to be discovered later on. But he knew they had to be there in order to account for this increasing level of complexity. Pretty smart guy. So this brings us to the condensation. You're probably all familiar with that term, condensing. We take a hot vapor like steam and we cool it, and it goes through the phase change turning into liquid water. It condenses. And that's kind of what we're seeing with the universe. We've had the Big Bang. We've got all this hot energy out there, and we're going to start cooling it down, and we're going to start to condense matter out of that hot energy. And as that matter starts to form, we get something else as a byproduct, and that's gravity. You can't have gravity without mass. And you can't have mass until you have matter. So as matter starts to form, we start to get gravity, and the denser matter, the heavier stuff, all starts to gravitationally move toward the center of the cluster. It's just centripetal force, laws of physics. So we start to see the matter that's forming moving through this nebula, this cloud of condensing matter and gas. And the heavier stuff's moving toward the center of this cloud, the lighter stuff's kind of being left along at the edges. And that means that as the heavier stuff accumulates in the center, that's where it's heavier, that's where there's more mass, that's where the gravitational attraction is going to be stronger, so it pulls in even more stuff. So the center of this nebula is growing. It's getting to the point where the stuff is piling in there, and it's got stuff that is just slamming in, giving off heat, and we're starting to develop what we call a Proto-Star. Beginnings of what a star is going to be. And this process continues. And as we're slamming all this stuff together, we're slamming hydrogen against hydrogen, fusing them together to make helium. It's giving off energy, and that center of this disk now is becoming even more and more like a sun. So we're basically making something that's starting to look like our solar system in a way. let me ask you this question. If this is happening and I'm building this proto-sun in the center of this nebula, what's its main job? Is the sun basically converting hydrogen into helium, and then it's going to convert that into all the heavier elements? True or false? Okay. Let's see what you think. Yeah. Yeah, basically, but it's not quite that simple. We're going to say true, because that's what's happening. We're fusing hydrogen into helium. That's the main thing, and it's mostly just hydrogen being made into helium. Eventually, we'll get to the heavier elements, but it's going to depend on what size the star is as to how far along that process we're going to get. Okay? That's kind of what stars do. This is a picture that was taken from the Hubble Space Telescope. This is one of the very first pictures that came back after the scope got adjusted and got its correct focus fixed. And this picture paid for the Hubble Space Telescope fix. Because what we see in this picture is the creation of the universe. If you look at it, these are the pillars of Hercules. These are in the belt of Orion, constellation of Orion. And these pillars are about 3 light years tall. So in other words, that's the distance light would travel at the speed of light in the 3D world. That's pretty big. And you see within this nebula, this gas nebula, therefore the nebula part of the theory, you can see these bright twinkling stars. And these stars are the beginnings of solar systems, the beginnings of our universe, which has had a number of these smaller events within it. We can actually see this type of condensation going on within this nebula here in this picture. Unbelievable. We've got evidence right there. So we've got these stars forming. These nebula are coming together, forming these stars. And in our solar system, our sun is nothing more than a star. It is the proto-star that's gone critical, become a full-fledged star. But our star is just a medium-sized star. It's not a biggie. It's a medium-sized star, and it's about halfway through its life. So if it's 5 billion years old, then it means we've got about another 5 billion years before our sun's finished. So as a medium-sized star, what do we expect from our sun? How did it form? Well, it started back here in this nebula, this cloud of gas and dust. As matter is coming together. The center started to grow. It formed the Proto-Star, and eventually that had enough material in it that it compacted enough, it had collided enough, it was giving off enough energy from hydrogen being burned and fused into helium, and there was some radioactive material that was developing, and basically our Proto-Star became what we call the main sequence medium-sized star. It will continue to fuse hydrogen into helium. That's going to probably be its main job for most of its life, giving off energy in the process. And eventually, it's going to run out of hydrogen. Just like your gas tank in your car, you can only fill it so full, and eventually it's going to run out. And when that starts to occur, just like when you're on the car and you start running out of gas in your car, trying to suck out those last few drops from the tank and kind of... Well, that's what the sun's going to do. And in the process, the very first thing it's going to do is expand. And it's going to shrink.